Hello everyone, welcome to the knowledge session. Today we will be learning about multi-threading in Scala. So before we deep dive into the session, let's take a look at knowledge etiquettes. So join the session 5 minutes prior to the session start time. We start on time and we conclude on time. Make sure to submit a constructive feedback for all sessions as it is very helpful for the presenter. Keep your mobile devices in silent mode. Feel free to move out of session in case you need to attend an urgent call. Avoid unwanted chit chat during the session. So let's move forward with our agenda. So we will going to discuss what is multi-threading, the benefits of multi-threading, problem we face with multi-threading, and in the later part we will see how we can achieve multi-threading along with its demo. So let's move forward with what is multi-threading. So as you can see, multi-threading is a model of program execution that allow for multiple threads to be created within a process, executing independently and concurrently, sharing process resources. Depending on the hardware, thread can run fully parallel if they are distributed to their CPU core, as it is an approach to execute the program on multiple threads simultaneously, and we can achieve it both asynchronously and synchronously. So as you can see, these are some threads which have some different tasks, and we can achieve multi-threading as different threads have their different tasks and they run asynchronously. So what is this thread? Let's see. So a thread is an independent unit of execution created within the context of a process. When multiple threads are executing in a process at the same time, we got the term multi-threading. So as you can see, this is the life cycle of the thread. So when the thread is created, it's over here in the start position, and then it will go in the runnable stage. After that, it will get the task, what the task it need to perform, and then it go to the running state. So after that, it might go to the blocked stage where it can be waiting for some operation, some task which are pending. Suppose some future value which might we will be getting in some time, and after that it again go to the runnable stage. Then it will complete the task, and then it got terminate. So let's move forward with the benefits of multi-threading. So I guess this guy doesn't believe multi-threading have some benefits. Let's see. So we do have some benefits. So this guy seems to be very happy. So we have some benefits, that is responsiveness, resource sharing, utilization of multiprocessor architecture, and economy. Let's move forward. So resource sharing. A single application can have different threads within the same address space using resource sharing such as memory, data files, etc. So as you can see, the this process have some CPU, some resources, some memory, and different threads are using the same process, uh, which which will optimize the process, which will optimize our resource. We can use multiple threads to uh, share the resource. Responsiveness. Program responsiveness allow a program to run even if a part of it is blocked using multi-threading. This can also be done if the process is performing a lengthy operation. So even if some thread is blocked, it will not gonna stop the program, or it will not gonna block the program. The other threads will run and perform the task asynchronously. Let's move forward. So the utilization of multiprocessor architecture. In a multiprocessor architecture, each thread can run on a different processor in parallel using multi-threading, and this increase the concurrency of the system. As you can see, this is the example of the multi-threading, and this is the example of the multiprocessing. In this, you can see there are multiple process which are available, but in this we have only one process, and multiple threads are sharing the memory and the resources. So as thread is a very lightweight sub process, the smallest unit of processing, it it is a separate path of execution and share the same resources. So uh, now let's move forward with economy. So it is more economical to use thread as they share process resources. As I told earlier, it is uh, more expensive and time consuming to create a process as they require more memory and resources. So that is why we will be that is why multi-threading is much more cheaper, and it is very convenient and less costly to create a thread and get the task done. So let's move. So we have some problems with the multi-threading. So I would like my co-facilitator to uh, share her screen and continue with the same.
So is my screen visible?
Yes, it is visible.
Okay. So as we discuss the what is multi-threading and then what are the benefits of multi-threading. Obviously, when there is some approach that is in the market, we generally have some problems to deal with it even. Now let's take a look at them. Okay, we all know that the life is so hard when we have to deal with problems. But don't worry, we will be also sharing some ways to achieve multi-threading later that will like resolve the problems. So generally, multi-threading goes through some problems like race condition, starvation, live lock, and deadlock. So moving on. Now, what is a race condition? In a race condition, threads access shared resources or program variables that might be worked upon by other threads at the same time, causing the application data to be inconsistent. So generally, there is a critical section in the program. A critical section is any piece of code that has a possibility of being executed concurrently by more than one thread of the application. And it exposes any shared data or resources used by the application for access. So, a race condition happens when threads run through critical sections without thread synchronization. Uh, the threads race through the critical section and try to read or write the shared resources depending on the order in which the threads finish the race. The program output changes as per the order. So, as we can see here, there are two threads, or there can be n number of threads that trace towards the critical section or a part of the program, uh, like in which we are writing a variable or reading a variable, and that changes the output of the program. Now, we come to live lock. Processes enter a state of live lock when they clash with each other's state and fail to progress because both of them are changing the state and having the same state at a given time. A live lock happens when two threads start taking actions in response to other threads instead of making any progress. The best analogy is to think that there are two person 1 and person 2. The person 1 is trying to reach out to person 1 and the person 1 is trying to reach out to person 2. They both person are changing the state continuously but are not able to contact with each other. So that is generally a state of a live lock. Moving on, we also have a situation of a deadlock. Now, firstly, we'll discuss deadlock and then I'll tell you a slightest difference between a live lock and a deadlock. So, deadlock happens when two or more threads aren't able to make any progress because the resource required by the first thread is held by the second, and the resource required by the second thread is held by the first. So, now you must be thinking what is a live lock and what is a deadlock. They seem to be quite similar terms. Now let me try to like decode it for you. Deadlock happens when it is when the one thread is acquired the resource which the other thread wants. So the whole point comes to the resource that is acquired. Whereas in the live lock, we can see it mainly deals with the state. So the two threads keep on changing the state, and they're not blocked because of the resource case. Okay. Now moving on, we are dealing with starvation now. Other than a deadlock, an application thread can also experience starvation where it never gets the CPU time or access to a shared resource because other greedy threads hog on to the resources. As we all know, when we start a multi-threaded program, all the threads start synchronously, and they just go and try to acquire a lock or try to like access a variable or a method that is like reading or writing something. So some of them might not get the resources or the CPU time, and then that case comes of starvation. Moving on. Now we have, as discussed, some of the problems that we deal with when we are doing a multi-threading. But now we must discuss what are the ways of doing multi-threading along with the demo. Oh, this guy wants to know quite quickly how are we doing it. Uh, since the topic of this knowledge session is multi-threading in Scala, so mainly we will be discussing ways to achieve multi-threading in Scala. Generally, there are two major ways of dealing with multi-threading in Scala, that is through futures and Akka actors. But there are two minor approaches as well, that is parallel collections and using the legacy JVM way, that is using the thread class and runnable interface. We won't go deep with these two concepts uh, in this session, but we will take a look at futures and Akka actors. For now, let me explain you what is a parallel collection. Then uh, it is like a normal sequence or a collection when but we try to access the values of that collection parallelly. Like if we have a list that contains 10 numbers, uh, li- uh, and we try to access them, then they are accessed synchronously. But if we make it a parallel collection, then those values will be accessed on the multiple threads, that is parallelly, all of them together. So moving on. Now we come to a point, what is a future? So a future, so basically, a future represents a value which may or may not be currently available but will be available at some point of time, or an exception for that value if it is not available. Some operations like database query or an HTTP call service can take a while to complete, and running them on the main thread would block the program execution and decrease performance for that purpose. So we have futures for them. Future represents a result of an asynchronous computation that may or may not be available yet. When we create a new future, Scala spawns a new thread and executes its code. Once the execution is finished, the result of the computation will be assigned to a future. So the result of the computation here will be assigned to the future. Now, a future, as we can see, is a carried function which has a body and an execution context. As we know that carried function means that it will take like two of the argument list. So here is the one argument list that contains the body of the future, and this is another argument list that will take an implicit value, that is the execution context. Now, what is an execution context? We'll see it here. And before we create any future, we need to provide an implicit execution context. This specifies how and on which thread pool the future code will execute. An execution context can execute the program logic asynchronously on a thread pool. We will discuss about thread pool later. So it is used to manage threads which are created by thread pools and manages tasks in the thread. The execution context is used to configure on how and which threads the asynchronous task future will run. Generally, we provide global as the execution context, which generally in between uses the fork join pool. We will see the types of thread pools later in the part of the session. but we generally take execution context is global when we are dealing with the future computations. Moving on. Now, what is a thread pool? As we discussed, like in the execution context, we provide a thread pool that manages all the threads and everything. So now see what's a thread pool. A thread pool manages a set of anonymous threads that perform on a work request. When we use a thread pool, we write our concurrent code in the form of parallel tasks and submit them for execution to an instance of a thread pool. This instance controls several reused threads for executing these tasks. As we can see, this is a queue of tasks and these are the threads. So basically, thread pool contains all the threads that are present. It can be of many types and we can see it later. So the task from the queue is assigned to one thread, and task 1 will be assigned to which thread is also decided by the thread. Moving on. Now, since we know that there are thread pools, now we must also know what are the types of thread pools. So, generally, there are like 5 types of thread pools: single thread pool, cache thread pool, fixed thread pool, fork join pool, and scheduled thread pool. As I've already told you before, when we specify the implicit of the execution context as global, we generally use fork join pool in that. So, now what is a single thread pool? Single thread pool has only one thread, so all the tasks are submitted to that particular thread only. So it can be like we are executing the program in a multi-threaded environment, but it is quite synchronous when we are using a single thread pool. Now, what's a cache thread pool? A thread pool that creates many threads it needs to execute the task in parallel. So basically, cache thread pool creates as many threads it's required, or like it is available for it to execute the tasks that are given. The old threads are reused for the new task. If the thread in a cache thread pool is not used for like 60 seconds, it will be terminated and removed from it. Moving on, fixed thread pool. A fixed thread pool contains a fixed number of threads. If the thread is not available for the task is put in the queue, and then it is executed later with the other tasks. Okay. So now we'll go to fork join pool. Fork join pool means a thread pool with a number of threads depending on the runtime dot available processor. Basically, it gives the value like how many threads a processor can support, and that value it gets, and for that purpose, it basically creates the thread that are in the fork join pool. So by default, we use fork join pool. Now, what's a scheduled thread pool? So, scheduled thread pool contains the thread when we want to execute some tasks periodically, like in a day or like in some part of the day, daily or maybe weekly. Then we use a scheduled thread pool for that purpose. Moving on. Firstly, let's see if we want to see the demo for futures. Just a second. Okay. So since we now know what is a thread pool, what is a future, what is a execution context, how are we using the execution context. So now let's take a look at the small program and how we are executing a asynchronous program or a multi-threaded program with the help of futures. So since you know, like this is my main thread, right? And this is my main thread, and I'm just trying to print the name of the current thread. I'm trying to get the current thread and just trying to print its name so that we know that what are the computations we're doing, what is the name of that thread. And as we all know that it will print main itself. Okay. So now the function that will double the value, but in future. Okay. So this accepts a list. So I've taken that list, and now we're trying to map all the values from the list uh, and trying to get the value of the current thread. As we know that when we try to put a value in the future, it generally executed on the other thread or like some other thread other than the main thread. So from this one, we'll get the name of what is the current thread is and on which the particular number or the value is being executed upon. Now the value that it is getting, and now it is trying to double the value. So basically, when this function will double the value from the list, but will return the future of that. And now since we can see the return type of this is string, so it will return future of string. And since we are giving it a list, so it will be sequence of future of string. Okay. Now you must be seeing that I've used a function name future.sequence. So let me take you through this. So future.sequence in simpler words will do. Let me take you through this, and then I'll try to explain you it in simple words. So simple version of future traverse asynchronously or non-blocking transformation, it essence is an iterable of future of A or any type into a future of this. This means like it is iterable. This is like iterable once of future of A, and it converts it to a future of iterable of A. So as we can see it here, as we can see the type here, let me show you. And let me not apply future dot sequence here. So okay. So as we know, the type of this is future dot sequence of string. But now when I've applied future dot sequence here, the type would change to future of sequence of string instead of this one. So as we hover on to the result and try to check its type, that is future of sequence of that. And now as you can see, it is returning unit because we are returning the string part here. Okay. So now I'll try to execute this program and try to explain you what we get the result and how we are getting it. And for that purpose, you must be thinking I have not applied for any implicits here as the execution context, but you can see I've exported or imported the global implicit that specifies that I'm using the fork join code here. So now let's run this program. Oh, you can see. Firstly, it is printing what is the main thread. It's printing the main thread. Now, it is taking one by one each of the values and it is executing on different threads. You can see it on thread number 13. It is taken the value 1 and it has doubled the value. Now, it has again taken on the thread 14. Now, as we can see, it has become a multi-threaded program because we are running the program on the main thread. We are executing one value on the thread number 13 and then again on the thread number 14. We can see the number of the threads change anytime as it is dependent on the runtime available processors. So each value on the thread is taken by different threads and is doubled in that way. We can try to run this program multiple times and see we can get a different value of the threads or different things every time. You can see now it starts from 14. Again, now it's an order. So as we can see, it is like a multi-threading through futures. Going back. I would like my co-facilitator Pallav to take and explain Akka Actors from here.
Hey everyone. So let's start with Akka. So Akka is Pragati. You can share your screen. Okay. Let me do it.
Okay, I'm sharing it. Just a minute.
Okay.
Yeah.
Okay. So Akka is a platform for designing scalable, resilient systems that span processor cores and networks. It allows you to focus on meeting business needs instead of writing low-level code to provide behavior and fault tolerance, high performance. So uh, let's move with the Akka actors. So Akka actor model adds a layer of abstraction that make it easier to write accurate, concurrent, parallel, and distributed system. Secondly, the Akka actor applies to the entire set of its libraries, thus allowing you to understand and use them consistently. So, an actor can easily write asynchronous code without the need of lock and synchronization. It helps to deal with explicit locking and thread management, some of the problems we face in multi-threading. So, hence making it easier to write correct, concurrent, and parallel system. Akka actors are object, and you can't access them directly, but only you can send message with them. An actor represents an independent computational unit, therefore it encapsulates its state and part of the application logic. So actors are isolated from each other, so they can only communicate through message. In addition, actors do not share their memories. So if the actor get multiple messages, so these are processed in FIFO order. Only one message is processed at a time. So moving forward, we can take the demo.
Yes. So moving on with the Akka actors, like I'll show you how we can do multi-threading with the help of Akka actors now. So here you can see, firstly let me show you, we have used this dependency for using the Akka actors, and we have not put the test dependency here as we have not written any kind of the test cases for this program. Moving on. Firstly, we need to create an actor system that we have created as the name of first actor system, and we can also print the name of the actor system. I'll show you that when I run the program. Moving on. Now, since we have created the Akka actor, we will try to send some messages to it, as Pallav told us that Akka actors communicate by sending messages to each other. So this is the receive method for the actor, which we will send messages to. And now we have like three cases in that. That is like add, subtract, and divide. So basically, we will be sending some message, and it will contain some numbers. And according to that, we will basically try to tell a method like what to do. So drilling down, we come like if we get the add condition here. So we'll basically print the sum of the two numbers. We can see that it is quite simple. In case of subtraction even, we will do the same. It is in the class of subtraction. So we will provide the difference of the two numbers here. Now, when we come to division, it will also do the same. Like it will divide the two numbers and give us the output. We will see this part of big computation later in the program. So coming back to the driver code. So as we know that this is the way I've created the actor, right? So instantiated the actor basically. Now I'm trying to tell a message to through this actor and trying to print this through the main thread. Now the purpose of this is this has to be done on the other thread. If the Akka actors perform computation asynchronously, then this will happen on the other thread. And if not, then it will wait for that computation to complete, and then only it will print this message. Okay. So now let's run the program and see what we get as an output. If we get the value of this first, or do we get this? Oh, you can see that. Let me expand it a bit. Yes. So firstly, the name of the characters print that we have provided in here. Then we can see that it is running from the main thread. That's the logger we have put into, and then it is again running from the main thread. Instead of executing these computations first, it is running the main thread computation. So that specifies that the messages we are trying to tell the actor are executed on other threads other than the main thread. Now we can see that we have called the add method here. So it is adding and giving us the sum. Now we are trying to subtract them, and it is giving us the difference as well. Okay, now we can see that we have called the divide function first, but still it is showing the sum method. Maybe because the divide one was taking a bit longer to execute, and we are doing it asynchronously on multiple threads, so it is not waiting. So here we get another point that it does not wait for any other computation to complete, and it executes other computations that are in line in the form of messages. So as we see, again it is printed the sum, and later the division part is printed, right? So let's try to rerun this program and see if the output of the program changes, because we are running it in the multi-threaded environment. So as we know, it changes. And we cannot predict basically what is the output of the program in a multi-threaded environment generally. Oh, we can see this now. The division thing is printed first, and now it might have executed the computation faster, and it has printed the later parts that way. Now, taking you through, suppose we have a big computation in this case of divide. Okay, and right now we don't have any big computation, so I'm just trying to put it, and this is just a case when we have a big computation, and I'm trying to sleep this particular thread of divide for like 1 second. Okay, so that will delay this computation. Now what we need to see is if it executes divide first or add first, as we're trying to delay this one. So will it print add or not, or will it be waiting until it does it for divide? Let's see it here. So as we can see, it has printed firstly all the things from the main thread, then it has printed things from the sum, then it has found the difference, then again it has computed the addition of these two, and then it has executed the division. So Akka Actors posed as the best way of resolving multi-threaded problems in Scala, as you can see it is not even waiting for other threads to execute. It is not even like coming into race conditions or anything like that. Not even in a live lock or deadlock condition. Obviously, we are not using the same threads or resources, so that is also a point of question. But it is not waiting for any other computations to complete. So, in general, futures and Akka actors are the ways to resolve multi-threaded multi-threaded environment code and in a best way. So, going back. So that was all for the session, and we are all open now for any kind of questions or queries if you all have. We would like to take them, and that's all from our end. Thank you everyone for joining the session.
Do share your constructive feedback so that we can improve, and we will come back soon with some new sessions. Thank you, and the stage is all yours if we have any questions.
Yeah, I have one question, Sudarshan this side. So, which execution context does Akka actors use internally? Do they have their own execution context, or it is the same execution context which is given by the Scala library?
Okay, so we generally use dispatchers for that purpose, I guess.
Dispatcher in the sense, like my question is like, does the Akka actors use the global execution context, or they have their own execution context, or they have defined their own execution context?
Generally we have dispatchers in case of Akka actors, and we provide them as an implicit. So they basically deal all the computations in case of Akka actors.
Okay.
Pallab, do you want to
We
take this
can
one?
also specify which we want to use. Like mostly we use fork join pool and like, fixed thread pool.
Mm-hmm.
Yeah, in case of all the computations, be it futures or Akka Actors, we generally tend to use fixed thread pool or fork join pool, as it provides us like much more utilization of the use resources. So
As fork join pool uses that creates the threads depending on the runtime dot available processors. So it is the best way to optimize the memory, and that's why in the global as well we use fork join pool.
Yeah, global it uses.
Yeah.
One more interesting question I have is like, I mean, what happens when we use multiple execution context in the application? Let's say in one part of the code we use global execution context, and in another part of the code we use different execution context, not the global one.
okay,
So, I mean,
so
how do we handle that one?
okay, so like as we know that execution context is a part of like implicit. So, and as we know that if we try to provide two or more implicits in the same context or in the same part of the code, then it will not take it, because the compiler will throw like it is ambiguous and it was not able to rectify like which implicit value it is supposed to take. And we all know that
No.
execution context.
I mean, I'm saying when we use it in a different class, or maybe in the same class we can use it. But I'm just curious to know how you know uh, threads are assigned and how the communication happens between the future and the thread pool, because we are using a different, I mean, two thread pools, right? Two execution contexts, different execution contexts.
Yeah, but if they are in the part of like if they are in the two different classes, then it would be separate, right? So it would execute simply like it was there in the program. It will not hinder the other part of the program, right?
Execution context is basically responsible for managing all the threads, so it manages by its own.
Yeah, but again, it is it's an object, right? So one execution context is one object, and other execution context is a different object. How do they communicate internally? That is what my question is. Let's say your class A uses global execution context, and your class B uses that's a different execution context. You said that fixed number of threads, right? So that execution context. So in that case, let's say your class A and B are interdependent. Then you have features to pass on, right, between the multiple parts of the code. How actually it communicates in between
So
I mean, how does it use?
we do have a context manager which does this task for the for us.
Okay, sure. Thank you. I think it was very nice session. Thanks guys for preparing and for having us here.
All right. Thank you.
Hi, this is Santosh here. So, do you have time to have some paid questions?
Yes, please.
Yeah. So, in terms of like we are using future for the asynchronous execution, correct? So
Yes.
we can attend the same thing in the Akka. So we know like Akka is developed from the Scala language. So Akka is also using the Scala. I mean futures implicitly.
I didn't get your question. Can you please repeat?
So we can use futures and Akka actors to implement execution. I mean the asynchronous execution, right?
Yes.
So while we're using Akka actors, like we know like this framework developed from Scala language. So is Akka actors also using the future implicitly? I mean from the framework code, library codes or jobs to implement the asynchronous operation.
So these two are different topics, but yes,
Okay.
they do uses futures as in the combined program, we need some future values,
Yeah, correct.
as it basically it is an actor model.
Yeah.
It is basically message passing, what we are doing with Akka actors.
Yeah, message-driven system. Yeah.
Yes. So dependency of Akka is futures is always there.
Okay. Because if you see in our project, right, as you said, like we are using execution context from the Akka actor dispatcher, but we are not using any actor that receive to use the asynchronous option. We are simply using the future execution context tag.
Yeah.
So I can see like we're using some actors, we're using receive method, right? So I got confused. Like, is there a two different entities to execute the execution context in the Scala code? So one more doubt is like we are using a forejoin executor. I mean forejoin pool in the Akka actors, because forejoin pools are different from the concurrency, right? We know like there is a difference between concurrency and parallelism, right?
Yes.
So is the Akka actors using the parallelism or concurrency, or it's implementing both?
Okay, so like I'm not very thorough with this, but I guess it's not using like concurrency; it is using parallelism.
Okay.
It, yeah, but there's no point of like concurrency or parallelism in that purpose, because like each actor is like has its own state and it is isolated from each other, and we
Yeah,
just
correct.
communicate by passing messages. So like
Using mailbox. Yeah, correct. Yeah.
yeah, and it is just managed by its parent actor, or it may be the root actor if it is the
Yeah,
first one. So
correct. Yeah.
no point of like threads or something, or it's completely isolated, not even sharing a resource, nothing, and just by executing by passing the messages.
Okay. Okay. Thank you so much. It's a good session actually. Yeah. Thank you so much.
Thank you. Okay, so I believe we are done. If you guys have any queries or questions, you can reach out to us. And
Thank you all
thank
for
you for
joining the session.
thank you. And we are closing the session. Thanks for the joining. Please do provide your constructive feedback for improving the session.